Okay, so this is a video solution for problem number 23.1 from homework 2. And part A states, what is the strength of the electric field at position indicated by the dot in the figure? And they've given us a figure that looks something like this, and then they gave us the length of x here, which is 7.0 centimeters. Okay, so first of all, I kind of relabeled my variables here. They had given us this x as r and d as r, but for calculating purposes, I've relabeled this as x and this as d, because for our equation we're going to be wanting to solve for this r here. So to not confuse myself, I switch those around. And then this angle here is going to be theta, which we're going to need to know. And yeah, so we have our charged particle here and our charged particle here, and they want to know what's the electric field strength at this point P from both of those charges. So to calculate electric field, we just need to use our electric field for a point charge equation, which is E equals 1 over 4 pi times epsilon naught times Q over R squared, and that's in the R hat direction. And so to calculate R squared, like I said, they've given us X, which is equal to 7 centimeters, and they labeled this as the same. So I know that these two are equal, so D is also going to equal 7 centimeters. And then, so to calculate R, we know we just need to use the Pythagorean theorem, and that's R squared equals that X squared plus the D squared. So we get R squared equal to 0.0098, and then plugging those numbers into that equation, we get our electric field strength from one of those point charges, or from one of those charged particles, as 2,752 newtons per coulomb. So we don't want to just take that electric field strength and double it, because we know we're working with vectors here, so we're going to need to break it into its components in order to figure out what the electric field strength is exactly right there. So because these are two positively charged particles, they're repelling each other, and because they're equal distances away, we know that that field strength in the y direction is just going to cancel out, because these two are going to cancel each other. So we only need to solve for our electric field strength in that x direction, or on the x-axis, in the I hat direction. So to do that, we just take our electric field and we times it by cosine of theta. So now we need to calculate theta, and that's going to be equal to the inverse tangent of x over d. So adjacent over, or opposite over adjacent. And then we get theta as 45 degrees. And now we can plug that in, and we just times our electric field strength that we calculated times our cosine of 45 to get it in just the I hat direction, and that's going to be equal to 1,946. And then we need to add both of those for Q1 and Q2. So for both of those particles, the electric field strength acting on that point charge is just going to be 3,892 newtons per coulombs in the I hat direction. And then for part B of the problem, they just want to know is what direction that electric field is going to be pointing. Yeah, what is the direction of the electric field at the position indicated by the dot in the figure? So we know that the y's cancel out. We're only going in the I hat direction, so the direction is going to be horizontal to the left, which I've indicated there. And yeah, This all ties into what we're learning in chapter 23 with electric fields and point charges.